Anyway, the idea for this ergodicity breaking is that basically at the thermodynamic limit, even for very small non-zero symmetry breaking field, it will basically eliminates half of the phase space in this Ising model. And because of the fact that when the little or the magnetic field or the symmetry breaking field is there, the symmetry related configurations actually have very special probability weights. And basically the ratio between these two symmetry related configurations will be exponentially large and in the system size. Therefore, at the thermodynamic limit, basically one of the Ising partners will basically dominates the symmetry related configuration, and that will lead to the fact that the phase space will become disconnected, and that's why we said the system has the ergodicity breaking. Okay, so are there any questions so far? Okay, so if not, let's try to. So here, let me switch the notation a little bit, and the reason that I switch the notation will become clear because it basically make the expression more concise. So the notation switch is that now the ferromagnetic coupling is defined such that the extrinsic coupling's magnitude is specified, and it will be greater than 0. And the dimensionless parameter for our system will be H and K as before, and the coupling should be a nearest neighbor coupling. And first we'll consider the one-dimensional system, so the coupling will be between the site at I and the site at I plus 1. Okay, so in order to solve this one-dimensional problem, in principle, we should derive the partition function. So let's start from the simple limit with open boundary condition. And in the homework, you actually have done the limit where h is 0, but with a periodic boundary condition. So in this open boundary condition, the result will be even simpler. So basically, when you write down the partition function with 0 external field and system with n spins, basically it should look like this. Okay, I forgot to sum over the i's. Okay, so that's the partition function, and as usual, we can notice that the spins basically is a binary variable. So the product of SI and SI plus 1 can only be binary variables also. So it will be plus 1 if the two spins are parallel. And it will be minus 1 if the two spins are anti-parallel. Okay, so that's quite straightforward. And the idea to solve this partition function is by realizing this particular relation. Then you can try to define a new bound variable. Maybe we call it eta. Now this eta is the value of this product defined on the bound I plus 1. Okay, so if you do that, basically the partition function will now be something like sum over all the possible etas, and now you will have this eta variable. Okay, and as usual, the bound number will be n minus 1. So when you perform this summation, you should see the partition function should be 2 times cos k to the power n minus 1. And the reason there's a factor of 2 is because we don't know what is the sign of the first spin, because if your eta is equal to plus 1, which suggests that there are actually two Z2 related configurations. Either it is two of them are both positive 1, or the two of them are both negative 1. And that will contribute this factor of 2 here. So that seems like easy, that we can solve the partition function of a one-dimensional Ising model. But this method is actually a little bit difficult to apply to the case when there's an external field, because you can immediately realize the trick doesn't work if you add another term that is related to h times si. So because of that, we're going to introduce a more general method, which is called the transfer matrix method. Okay, so this approach will allow us to derive the partition function for one-dimensional Ising model with non-zero external field. Okay, so let's start. So the idea is that when we are right now the partition function, it seems like maybe there's a chance that we can list all the possible configurations and try to add up all the Boltzmann weight in a systematic fashion, because it seems like the system is just so regular and simple looking. So maybe let's just try to focus on one bound. Say maybe we are focusing on this the bound that connects side I and side I plus 1. So if we write down all the possible configurations for this two-side problem, and let's try to use the order that the first spin is always represent the spin on the side I, and the second spin is always the spin on the side I plus 1. Then there are 4 possible spin configurations. And now I intentionally arranged them in a matrix form. So you can see that the row index is basically the spin configuration on side I, and the column index is basically the spin configuration on side I plus 1. So if we do so, and maybe we can try to write down the corresponding Boltzmann factors. So for the two spins aligned in the same direction, the Boltzmann factor should be exponential k plus 2h. And the factor of 2 is because there are two sides, and there's only one k because there's only one bond for this two-side problem. So for the case that two spins are flipped, basically the bond energy is still the same, but the energy due to the external field will be flipped. Okay, so that's the diagonal terms. And for the off-diagonal terms, because the energies induced by external field basically cancelled, so all we have is the bond energy related to K. But because now the product is -1, so the energy is opposite with the parallel spin configuration. And similar arguments suggest the other left element to be exponential minus k. So we realize that for this two-bond problem, we can try to elaborate or like it enumerates all the Boltzmann factors and try to arrange them such that the index correspond to the correct configuration. So if we try to think about this problem for the bond I minus 1I, which is like the bond that is at the left of the previous bond, basically we will get a similar expression. But now the spin index is a little bit different. So it is very tempting to say that maybe we can try to make some kind of matrix multiplication such that we can take care of the spin configurations automatically, as we have did in the previous non-interacting systems, where we basically expand the exponential of the total energy by products of the Boltzmann factors with each individual modes. So we are trying to carry that idea, but if we try to think a little bit harder, we realize that the magnetic field here, basically the magnetic field apply on side I, is counted twice if I try to use this particular matrix representation. So in order to avoid the double counting, the simplest way to solve this difficulty elegantly is to consider the case where you have basically periodic boundary conditions where all the spins are coupled with two neighbors. And if it is so, then in order to avoid the double counting, what we can do is that we can simply say I just reduce the factor of 2 by 1. Okay, so if we do that, the correct matrix that will give us the correct partition function should be this matrix T. And this matrix T is defined on the bond connecting site I and I plus 1. Okay. And now we will try to use this matrix T, which is what we call the transfer matrix, to express our partition function. I will continue this process in the next lecture. So let's take a 10 minutes break. I think we will continue. So in the last lecture, we basically try to start from scratch to understand why transfer matrix is possible, because it seems like we can very effectively arrange the Boltzmann factors as some kind of matrix. And the advantage of doing that is, of course, we can order our Boltzmann factors systematically, but we also realize that in order to make the whole process applicable, we need to be careful about the energetic cost due to the external field. And the reason that we can overcome this fact is because the inconsistency actually come from the double counting of this magnetic field effect. So we can simply correct that by reducing the factor of this exponential factor by a factor of 2. So we successfully construct the transfer matrix, and once we are able to do that, then the partition function can be expressed in this fashion. Let's just consider we have n spins, and we also know that the system is translationally invariant, so every transfer matrix is basically identical. So I'll just use T to express that. And the Boltzmann factor between the coupling of spin 1 and 2 is basically the matrix element of S1, S2 of this transfer matrix T. And similarly, we can use the idea to get the Boltzmann factor for the spins S2 and S3, and continue this process. We will basically use the periodic boundary condition to couple the last spin and the first spin. So if you express the partition function in this way, then you can realize that the expression here is nothing but the matrix multiplication of this transfer matrix and raise it to the power n. And the rest of the index, if you perform this matrix multiplication, is the last one. And when you sum over such elements, it actually corresponds to the trace operation of this transfer matrix raised to the power n. So that's a very concise description about the one-dimensional Ising system under the external field. So the question is how to evaluate this trace. And in the general situation, it will be difficult, but as we know, trace is independent of the basis, so we can try to find a basis such that the transfer matrix is actually diagonalized as a matrix D. So we want to diagonalize the transfer matrix T. And the reason we want to do that is because if we successfully do that, then the power T to the N will become a trivial expression. Let's assume, let me try to express what D is. Let's assume after the diagonalization, D is basically a 2x2 matrix that contains two eigenvalues, lambda 1 and lambda 2. So if it is a diagonal matrix, then T to the power of N will be simply lambda 1 to the nth power and lambda 2 to the nth power at the diagonal elements. Then the trace of this matrix is simply the summation of these two contributions. Then what we found is the partition function z is basically lambda 1 to the power n plus lambda 2 to the power n. So the question that is left is how to derive the eigenvalues, but that's a simple exercise for 2x2 matrix. So I'll just write down the solution for you. Basically, it can be expressed by a bunch of Cauchy and Sinch as usual. Okay. So now we are going to take the second step, that if we assume lambda 1 is greater than lambda 2, then this partition function basically can be approximated by lambda 1 to the power n, because at the thermodynamic limit, basically n is sent to infinity, and the greater one will basically be the one that is dominating, because we can actually express this summation is actually by this expression, and it will be approximated by lambda 1 to the power n. Okay, so that means that at the thermodynamic limit, if we can find the two eigenvalues are different, then basically the partition function is dominated by the one that has a larger eigenvalue. So let's see how it looks like by calculating the free energy of the system. So let's first start from the simple limit. When we send T, the temperature goes to 0. So when temperature goes to 0, we know that basically beta goes to infinite, and similarly K, which is defined as beta J, will also goes to infinite. So the free energy density, which is the free energy divided by the system, after you plug in the fact that the free energy is minus KB times the partition function, and the partition function is essentially related to the eigenvalue of the transfer matrix, you will realize that the free energy density looks like this. Here I didn't take the temperature goes to limit immediately right here because within the nature log there are still some dependency on the temperature. So here, because temperature goes to 0, this exponentially decay factor, exponential minus 4k, can be ignored. So the square root of sinh square will basically give us the absolute value of sinh. So if you input the definition of sinh and cos and consider the case when the magnetic field is greater or smaller than 0, you'll realize that this the quantity inside the bracket is actually this, and it can be simplified as exponential to the absolute value of h. And by evaluating the nature log function, what we got is the free energy density actually equals to minus j plus the absolute value of h. So we can plot that. Then it actually suggests a non-analytic behavior when h goes to 0. So as we mentioned in the previous case, that when t is 0, there should be a kink-like behavior in the free energy because of the level crossing. And now we can explicitly see why it is so. So similarly, we can ask what happened when the temperature is greater than 0. And this condition suggests the factor that is dropped previously cannot be neglected. So it will be a small but positive number inside the square bracket. And because of that, when you take the square root, basically this quantity will always be smooth. And because of that, the free energy of the 1D Ising model at finite temperature will always be analytic in H. So no finite temperature phase transition. Okay, so now we really recover the phase diagram of the one-dimensional Ising model with external field H. So let's remind ourselves what we have. So basically, because of this kink behavior, maybe I should use the same notation. Because of this kink behavior, we know there will be a level crossing at t equal to 0 and h equal to 0. And the magnetization will basically go from some value that is smaller than 0 to some value that is greater than 0. And once we pass the 0 temperature limit, basically everything is smooth, and it means that it must be smoothly connected with the high temperature limit, where all the spins are basically fluctuating and not forming order. So now we have the phase diagram. Are there any questions? Okay. So if not, let's try to continue our discussion. Previously, we argued that in 2 dimensions, the situation will be different. It will be a phase transition. So we will ask, is it possible that we can also try to go beyond 1D and try to push our calculation? And it turns out that the transfer matrix doesn't work beyond 1-dimensional, because the method just cannot be easily generalized to the case where the single spins can connect with multiple neighbors. So unfortunately, the transfer matrix trick does not work anymore. So because of that, we will actually introduce the idea of mean field theory. Okay, so the mean field theory is kind of important because first, it is the simplest self-consistent way to study interacting problems. So naively, we will think maybe it is very limited, but it turns out that it is quite general. And it can be applied to systems with very different physical condition. So it can be applied to various different various systems. Okay. And the third point why mean field theory is important is because there's usually a guess based on the physical arguments about it. So to some extent, the mean field theory has the ability to link your physical picture with the formal description of your system. However, it seems like there are so many advantages, but there are also some disadvantages of this approach. The most important thing is that it may not be robust. That is, maybe you can get some solution that is actually not really the robust configuration of the system. It can be destroyed by some other effects, such as the fluctuation that is ignored in the mean field approach. And even worse is that the approach may be qualitatively wrong. Okay, so you'll see why I said the result could be qualitatively wrong. So we'll try to introduce two types of mean field theory approach. One is also in the take-home project. That is the Weiss mean field theory. So the Weiss mean field theory is essentially the mean field description for Ising model on the hypercubic lattice. So let's see how it works. Okay. So the first step from the Weiss mean field theory is a simple observation that our Hamiltonian should look like this. And because the spin is now coupled with its nearest neighbor, and because we are discussing a d-dimensional system, let me just write it here. And that means that the single spin no longer just coupled to two of its neighbor. Now it could couple to maybe 4 or 6 or more other neighbors. Okay, so in principle, the difficult part is how to deal with this term, which is the interacting part. However, if j is 0, or like if we ignore the interacting part, actually we can understand why it's happening, because the magnetic field simply just give us a energy difference for the up and down spin configurations, and those spins will basically not discussing with each other because the Hamiltonian couple them on site. So because of that, we know one limit, that is if j is set to 0, we know how to solve the system. It is just a bunch of two-level systems. And we have done that calculation many times, so I'll just write down the conclusion. Basically, the magnetization of the system is equal to this hypertangent H of beta times the field H. By the way, in order to avoid confusion, the Hamiltonian will just use H omega to represent it for the system omega. So that's the first observation we have. And the second observation we have is that we want to ask how to understand the behavior of this term that the two spins actually can couple with each other. Okay, so here I intentionally focus on the JSI term. The reason that I try to focus on this term is because if we try to think about this term as some kind of field, then this exchange term can be considered as effectively it is providing a magnetic field effect, just like the external field term to influence the spins sitting on side J. So this is like the rough idea that we want to proceed. And but there's still some difference, because now the first difference is this effective field-like object now depends on the dynamical variable SI, which means that it is not, to some extent, it is not static. It has some statistical distribution. So that's the first thing we notice. And the second thing is that we still want to understand how to formulate this kind of abstract thinking in terms of equations. So how to do that? So here's the non-trivial trick that we'll try to describe the effect. So the idea is that if we just stare at the two spin interacting with each other, it basically is minus J times SI Sj. So if we try to rewrite Si in the following way, it will look like minus J times Si, subtract the quantity, and this quantity is the expectation value of Si, and times Sj. So to some extent, we just oops, I think I have a mistake. To some extent, we are doing nothing, because we subtract a quantity and we add this quantity back. And at this moment, this quantity is the expectation value of the I spin, but the evaluation is according to some probability distribution function that we don't know what it is yet. But we can still always write down this expression because it is a do-nothing expression. Okay. So at this moment, it is a exact expression. So the Weiss mean field basically make the following assumption, that this term to some extent is asking what is the fluctuation of the spins on side I with respect to its average value. So if we are really in the physical picture that the spins J times Si act like some kind of field, basically what we are asking is we ask this fluctuation to be very small and approximately 0. If so, then basically we can replace the expression summation of ij J times Si Sj by this summation. And here, the index I only goes through those sites that is nearest to the site J. So we can perform this summation because it basically counts how many neighbors for the site J. So usually we use Z, which is the coordinate number, to express this sum over I effect. And in the hypercubic lattice, Z is basically 2 times the dimensionality. But we'll leave it as Z, then effectively we will have something that looks like that. Okay. So now we can see the interesting analogy, because now this Hamiltonian can be almost equivalent to the case when J is set to 0, because effectively this coupling J induce an effect that is very similar with the external field, because they only couple with one spin sitting on side I, but here it's like a coupling for spin sitting on side J, but because J and I are both dummy indexes that label the lattice sites, so equivalent, so basically they are equivalent. But anyway, if we make this approximation, the Hamiltonian will be approximate as this. Here, the effective magnetic field is basically the true external field plus J times Z times the expectation value on side I. So so in principle, one should be able to solve this particular effective Hamiltonian, and the result will be the magnetization, which is the expectation value of spin on side I, should be determined by the expression that we had, but all we need to do is we replace the magnetic field by the effective magnetic field. So this is the self-consistent equation to determine what is the solution of the mean field theory. So let's try to dial back. So what we said is that we know how to solve the situation with only external field without the coupling. So we set J equal to 0. So that's the case we know. And once we solve the partition function, we can derive the corresponding probability distribution and then calculate the corresponding magnetization. And we found the magnetization will be hypertangent function of beta times the external field H. So the Weiss mean field theory is basically notice the fact that the coupling between two spins, to some extent, if you try to think about it as some kind of field, but now it is generated from the internal dynamics of the little spins. So if you use this physical picture and try to formulate it in a way that you ignore the fluctuation of your system, because now you assume you calculate the expectation value according to some distribution function. At this moment, we don't know what exactly is this distribution function, but let's assume it is there. And if it is there, then what we found is that its effect is basically it provides a additional contribution to the field by this expression. Because of that, our problem is again almost identical with the case with no exchange coupling J, but now it is a system with a modified magnetic field where the information of exchange J is included. So we use that system with this modified external field, and we ask what is the corresponding magnetization. And because it is identical with our previous problem, all we need to do is we substitute the magnetic field by the magnetic field with this exchange coupling correction. And as I mentioned, it will be a hypertangent function, and we require the magnetization of this particular system to be identical with the magnetization that we propose to start with. So in principle, if there's a solution for this self-consistency equation, then we said that we find a appropriate distribution function that we can use to approximate the distribution function of our original system. Okay, so that is the Weiss mean field theory in a very quick and dirty way. And once you know how to perform this self-consistency calculation, or once you find the corresponding value of M, then you can insert that into your description of the distribution function and evaluate all other possible physical quantities. So that's basically part of the work about the take-home project. So now I'm going to switch to another more formal description, which is the variational method. Okay, so this variational mean field theory to some extent is the formal structure of mean field theory. So previously, the Weiss mean field theory is described specific to the Ising system. So to some extent, we can form this kind of mean field theory description quite easily, is because this model is simple. So it is kind of easy for us to spot what is the starting point. So the question that we want to ask is that maybe we will have another Hamiltonian that describes another system, and maybe the non-interacting limit is still understandable, but with a more complicated form. How should we develop a mean field type description for these more general systems? So that's the reason I want to introduce this variational mean field theory. So to some extent, it is the mean field theory in a formal sense. Okay, so let's see how to proceed. So the first thing that we should notice is there's a inequality. Okay, and this inequality is easy to prove. Basically, what you need to do is, again, you try to express this expression using a do nothing expression. So you can see we multiply a factor which is exponential of the expectation value of f of x, and then we divide it again. So basically we are doing nothing. However, when we are evaluating the expectation value, because this quantity is just a constant, so we can pull it out. And now we are evaluating the exponential factor. And here we are going to use the fact that exponential of anything is greater than or equal to 1 plus anything. So we will have this expression. Okay. So again, the expectation value of f of x is just a number. So when we take the expectation value, the stuff inside the parentheses will basically be 0. So we got our result that we want to show. Okay, so now we are going to use this relation to develop the mean field theory description for a generic system. So to do that, the first thing is that we notice that the partition function of the system that we are interested in, maybe it is some spin system, so we'll just use spin SI to denote the degrees of freedom, but in general it can be any other kind of degrees of freedom. Okay, so by definition it should be just the Hamiltonian with those microscopic degrees of freedom to form the Boltzmann factor, and that will be the partition function that we want to evaluate. However, as what we did previously, we can assume that there's a Hamiltonian that is closely related to the physics that we want to describe. Let's denote this Hamiltonian to be H naught. And again, maybe I should give the Hamiltonian a subindex to distinguish it with the external field. So again, we want to subtract and add back this reference Hamiltonian that we know how to evaluate. Okay, so this is the exact expression of the partition function since we are doing do nothing operation again. You might think, why should I do that? If I do this do nothing operation, what is the advantage that we can get? And it turns out if you modify the expression a little bit, you will see the expression is actually closely related to the expectation value of a observable weighted using the reference Hamiltonian's distribution function. So what do we mean by that? So here we define the zero knot, which is the partition function of the reference Hamiltonian, which is the Hamiltonian that we know how to solve, and we to some extent know the physics there pretty well. So Z naught is basically the partition function for this Hamiltonian H naught. So if you divide this expression by Z naught and multiply it by Z naught again, you immediately see that the term that we add and subtracted actually will provide us a probability distribution expression in the summation over the microscopic configuration, which suggests the partition function can be considered as the partition function of the reference Hamiltonian times the expectation value of this Boltzmann-like factor, also related to the reference Hamiltonian, and the expectation value is taken with respect to the probability distribution function generated by the Hamiltonian H naught. And that's why the expectation value here, I add the sub-index 0 to denote this physics. Okay, so that is good, because once we are at this step, we are able to use the inequality that we just proved, which suggests that the true or the interacting partition function must be greater than or equal to the reference partition function times the exponential minus beta times the difference between the interacting Hamiltonian and the reference Hamiltonian's expectation value. So what does it mean? It means that by choosing the reference Hamiltonian, basically we are choosing the reference partition function. And no matter what kind of choose you make, you basically you will get an expression that is smaller than the original interacting partition function. So this whole expression, we define it to be the mean field partition function, and this inequality will also lead to the inequality in free energy. We will discuss that after the 20 minutes break. So if you have questions, please let me know.